Hello everyone. Today I will introduce one of the central ideas in analyze limits. More precisely, we will study how mathematics describes approaching behavior. In this lesson, we will focus on the definition of limits for a sequence. In previous discussion, we developed several fundamental tools of analyze. Completeness of the real numbers, supremum and infimum, the Archimedean property, density of the rational numbers. This concept allows us to describe the structure and distribution of real numbers. Although these ideas are powerful, they still describe only static information. For example, a set may have a supremum, but its elements do not necessarily approach that value. Similarly, supremum and infimum describe. Suppose we are given a sequence an. We would like to express the idea that an becomes arbitrarily close to some number L. This means for every arrow range, there exists a stage after which all terms remain inside that range. This is the central idea of a limit. This is an converge to L as n approach to infinity. Okay, we give this definition. A sequence of real numbers xn is said to converge to a real number a in real numbers if for epsilon greater than 0 exists n in natural numbers such that n is greater than or equal to n implies the distance between xn and a is less than epsilon. We write limit sub n to infinity x sub n is equal a. Why do we introduce epsilon greater than 0? The idea of a limit is to make the pairs approaching a value mathematically precise. First, approaching must allow arbitrary fine control. Therefore, we introduce epsilon greater than 0, which represents an arbitrary arrow range. This means we do not merely ask whether the sequence gets close to A, but whether it can become as close as we want. Why do we need n? Getting close once is not enough. We want the sequence to remain close after some stage. Therefore, we introduce an integer. N is belong natural numbers. Once n is greater than or equal to n, all later terms satisfy the distance between xn and a is less than epsilon. In other words, the sequence eventually stays inside the arrow range. Finally, the condition must hold for epsilon greater than 0, not merely for one particular arrow range. Therefore, the definition says after some stage, all terms of the sequence remain inside every prescribed neighborhood of A. This is precise mathematical meaning of approaching a value. Okay, let's look at this example. Prove that 1 over n is approach to 0 as n is approach infinity. At an intuitive level, 1 over 2 and 1 over 3 and 1 over 4 and so on becomes smaller and smaller. So we accept the sequence to approach 0. However, in analyze, intuition alone is not enough. We must prove that the term eventually stay inside every arrow range. To prove 1 over n approach 0, we begin with an arbitrary epsilon greater than 0. Our goal is to make the distance between 1 over n and 0 is equal 1 over n is smaller than epsilon. Thus, we want 1 over n less than epsilon. Equivalently, n is greater than 1 over epsilon. Therefore, we choose an integer n satisfy n is greater than 1 over epsilon. Then every n greater than or equal than n automatically gives 1 over n is less than epsilon. This is the core strategy of the proof. Conclusion: the definition of a limit transforms the intuitive idea of approaching a value into a precise mathematical statement. The key idea is not merely getting close once. Instead, we require that, after some stage, all later terms remain inside every precise arrow range. This idea becomes one of the central foundation of analysis and will later lead to continuity, derivatively, and integration. Thank you, everybody.